Today's topic is about georeferencing raster maps. This type of operation, although less and less frequent, still plays a fundamental role whenever we come across a map in analog format or a map in non-georeferenced digital format, which we want to use in a geographic information system. Georeferencing can be carried out in two generic ways. One makes use of control points whose coordinates are known. The alternative method uses control points identified simultaneously on the map to be georeferenced, and on maps that have already been georeferenced without the explicit use of coordinates. For now, we'll deal with georeferencing from control points with known coordinates. To do this, we'll use this schematic map, which I'll refer to as Map 1, which we'll load next. This map schematically represents points, lines, and polygons, all of which are clearly labeled. If the symbology seems different from what you have seen in the image, you can change the symbology without stretching the color scale. By default, loading rasters triggers a check for the existence of the corresponding pyramids. If you have deactivated the option to create pyramids, as in my case, you can force their creation using the Build Pyramids tool. Pyramids are used to improve visualization performance. They are a downsampled version of the original and can contain many downsampled layers. Pyramids can speed up the visualization of raster data by retrieving only the data at the specified resolution needed for the visualization. With pyramids, a low-resolution copy is quickly displayed when drawing the entire dataset. As you zoom in, levels with finer resolutions are drawn, but performance is maintained since you are drawing successively smaller areas. The database server automatically chooses the most appropriate pyramid level based on the user's visualization scale. Without pyramids, the entire dataset must be read from the disk and resampled to a smaller size. This is called resampling the screen and occurs when the screen is updated. Pyramids only need to be created once per raster dataset. After that, they are accessed whenever the raster dataset is visualized. The larger the raster dataset, the longer it takes to create the pyramid set, but the subsequent visualization will be faster and save time in the long run. The pyramids are stored in one or two files, which by default are in the same location as the source raster. These files are an overview with the extension OVR, short for overview, and a reduced resolution dataset with the extension RRD in the case of ERDA's Imagine format images. ArcGIS can read both types of pyramid files, but will only write OVR files, with a few exceptions. For more details, consult the ArcGIS documentation, searching for the term ArcGIS Pro Raster Pyramids. In addition to this, you may have noticed that the map load was accompanied by a message warning that the map did not have a recognized coordinate system. For now, we don't need to worry. We know that the map is not georeferenced and our aim is precisely to georeference it. If you change the coordinates of the cursor's location to meters and place the cursor in the bottom left-hand corner of the image, you will see that it is very close to the 00 coordinate point, and that none of the control points are in the position indicated by its coordinates. In other words, they realize that Map 1 is not georeferenced. Furthermore, for georeferencing to be carried out correctly, the view must adopt the coordinate system in which the coordinates of the control points of the map to be georeferenced are expressed. This being the case, our next concern must center on knowing the coordinate system of the map we want to georeference. In the case of Map 1, since it is a schematic map, you can check the inscription on its base, which identifies the Hayford-Gauss-Lisboa system. As a general rule, this is determined by consulting the map's metadata. So, the next step is to configure the view's coordinate system. Selecting the Lisboa-Hayford-Gauss IPCC system. Having established this very important first step, we can now move on to defining the control points. We start by making sure that the raster is selected on the Contents panel and proceed to open the Imagery ribbon, followed by Georeference. This section contains a series of tools. The first one we're going to use is the one that allows us to define control points. Analyzing the map, we see the presence of 4 positions, located at the 4 outermost vertices of the image, whose coordinates are inscribed. Note that the coordinate written vertically corresponds to the x-coordinate, and the coordinate written horizontally corresponds to the y-coordinate. We must first mark the position on the map to be georeferenced, and only then mark the corresponding real position. To ensure an adequate position, it is mandatory to zoom in on the position of the control point and only then define it. The position is signaled by a small red square, which remains connected to the cursor until the corresponding real position is defined. This actual position can be defined by clicking on the corresponding coordinate point, or by using the Target Coordinates command activated by the right mouse button. Continue by entering the coordinates. X equals 20,315 and Y equals 174,810. Under normal conditions, the map should disappear from the view area since the Auto Apply option is activated. In other words, whenever control points are defined, ArcGIS automatically adjusts the position of the map. As in this case, the coordinates entered were located outside the view area. When adjusting to the first control point, the map disappeared. In these circumstances, perhaps the most practical way to center the map on the view is to execute the Zoom to Layer command. As we have only defined one control point so far, ArcGIS has simply translated the map to match the control point on the raster with the actual position of the control point. Repeating the procedure, we should now zoom in on the area around another control point. The sequence of control points is perfectly random, although it is advisable to choose a diametrically opposite point, to avoid the alignment starting at points that are collinear with the x or y axis. Having achieved an adequate magnification, we can then repeat the procedure. Once again, the view has gone blank as a result of adjusting this second control point. Before proceeding with the georeferencing, I'd like to show you another important aspect. The Control Point Table command gives you access to the link table, where the georeferencing information is compiled as the control points are defined. The source X and source Y columns show the coordinates of the control points defined on the raster. The Map X and Map Y columns show the corresponding actual coordinates. If you have made a mistake in defining the control points, particularly when entering their coordinates, you can correct it here. On the other hand, if the control point had been defined incorrectly and you wanted to cancel it, you could select it and order its removal with the Delete Selected tool, present in both the link table and the ribbon. The rightmost columns refer to the residual errors in X and Y, and the average residual error for each control point. The error is the difference between the location that the point defined on the raster occupies, and the actual location that was matched to it. In the top right-hand corner of the view, among other things, the forward, inverse and forward inverse mean squared errors are visualized. The forward residual error shows the error in the same units as the map. The inverse residual error shows the error in pixel units. The forward inverse residual error is a measure of the closeness of your accuracy, measured in pixels. All residuals closer to 0 are considered more accurate. Although the mean squared error is a good assessment of the accuracy of the transformation, a low mean squared error should not be confused with accurate georeferencing. For example, the transformation may still contain significant errors due to a poorly entered control point. The more control points of equal quality that are used, the greater the precision with which the polynomial can convert the input data into output coordinates. Typically, the adjust and spline transformations give an almost zero mean squared error. However, this does not mean the image is perfectly georeferenced. For more information on georeferencing, please consult the ArcGIS documentation, in particular the overview of georeferencing page. For now, all the values are 0, but for the transformation by first-degree polynomial, from the fourth control point onwards, they must take on non-zero values. We'll see later. For now, let's close this table and go back to defining the remaining control points. Once again, we expand the area around a new control point, define its position on the raster, and enter the corresponding coordinates. Returning to the links table, we see that the residual errors remain 0. This is due to the way this transformation works: translation, rotation, and scale adjustment. In other words, with these three operations, it is almost always possible to make the points on the raster assume their real coordinates. Let's move on to the fourth control point. Returning once again to the links table, we can see that we have non-zero residual values, albeit very small. As I told you earlier, these errors represent the difference between the coordinates of the real positions we entered for the control points and the coordinates they assumed. Note that from a mathematical point of view, it's easy to get a point to assume a certain position. All you have to do is translate, as happened with the first control point. Requiring a second control point to assume the desired position isn't too difficult either. Simply hold the first point in the previously defined position, and rotate and zoom in and out of the map to check the position of the second control point. For maps like the one we're georeferencing, checking the position of a third control point is still generally easy to achieve. It's enough to adjust the scale along the x and y axes, but from the fourth control point onwards, the conditions to be met are much more demanding and small errors start to occur. Thus, to minimize the overall error, the small partial errors are distributed over all the positions of the control points. Under these conditions, by having more than 3 control points, which is the minimum number for this transformation method, it would be possible to select the control points with the highest errors and deactivate or eliminate them. We'll look at this later with another georeferencing method. For now, we'll use all for defined points. On the other hand, it's important to try to assess the quality of the georeferencing according to the values of the residual errors, in particular the forward mean square error. As you can imagine, any small error made when defining the control points must be evaluated according to the scale of the map that is to be georeferenced. For example, suppose the map is on a scale of 1 to 10,000. In that case, this means that a measurement of 1 centimeter on that map will actually correspond to a distance of 10,000 centimeters, or if you prefer, 100 meters, or even that 1 millimeter will correspond to a distance of 10 meters. Human vision tends not to be able to distinguish distances of less than half a millimeter under perfect conditions. By this, I mean that if we make an error of around half a millimeter in locating the control point, this error would correspond, at a scale of 1 to 10,000, to an error of 5 meters in reality. In other words, for the map at a scale of 1 to 10,000, an average squared error of less than 5 meters would probably mean that the georeferencing was acceptable, assuming that the control points were chosen correctly. Note, however, that if the scale were 1 to 50,000, the same half a millimeter would now be equivalent to 25 meters. I'd like to add another detail. In practice, I use the value of half a millimeter to assess the quality of georeferencing. However, it is possible to find bibliographical references that propose a value of 0.2 millimeters. Regardless of the value adopted, in the case of the map we are referencing, the residual errors are very small, practically zero, because the map is very special. It was created from a CAD map and exported digitally, which means that it has not suffered the deformations to which paper maps are subject due to variations in temperature and humidity, nor the deformations that generally occur in the rasterization process. The errors we observe are therefore solely the result of the inaccuracies we made in defining the positions of the control points on the raster, which is why they are so small. Before we finalize the georeferencing itself, I would like to draw your attention to 2 or 3 important aspects. One concerns the distribution of the control points. They must be evenly distributed throughout the map, that is, they must not be concentrated in one part of the map. On the other hand, the position should, as far as possible, define directions that are perpendicular to each other. I would add another detail. The control point should be located both on the outermost part of the maps and on the innermost part. Adjusting the periphery generally means that the innermost part of the map should also be well georeferenced. The opposite is not always true. Before finalizing the georeferencing, you can also save the values from the link table. This will allow you to redo the georeferencing later if you wish. To continue georeferencing, execute one of the save or save as new commands to save the georeferencing itself. The save command saves the georeferencing information with the raster and its auxiliary files. The save as new command creates a new raster map with the georeferencing information. Another important operation is to issue a report on the georeferencing. This report identifies the map, the transformation used, how many of the total control points were used, the root mean square errors, and the information on the control points. To finish georeferencing, we execute the close georeference command, which closes the ribbon. From now on, whenever you load this map, it will be displayed in the correct spatial position. Before I finish, I'd like to give you a particularly important note when working in a team. The same person cannot georeference the same map in the same way on different attempts. This means that if there are maps to be shared as a team, any raster should only be georeferenced once, and the information resulting from this operation should be shared by the whole team, rather than each team member doing their georeferencing. Finally, I'd like to show you the contents of the 2 files that were created by the georeferencing operation. The first is the XML extension file. This file was created from the moment we authorized the pyramids, but the referencing information has only just been included in the file. Its contents show the information on the coordinate system assigned to the map, as well as the set of coordinates of the control points defined on the raster, and the set of coordinates of the corresponding real control points. The second is the world file, labeled map01.tfwx. World files have the same name as the image, replacing the extension with a combination of the letters of the map extension, and adding the letter W at the end. Since version 9.2 of ArcMap, this extension has ended in X. These files can be used by versions before ArcMap version 9.2, as well as by other GIS software packages, simply by removing the letter X from its extension. For more information on world files, please consult the ArcGIS documentation, specifically the World Files for Raster Datasets page. That's all for now. See you soon.